In Chapter 22, we're investigating the electric field. How you doing out there? All right, now let's go back and review a couple ideas that we have. We know in gravity land that force is equal to big G m1 m2 over r squared. And electric field, we have in electric land, we have a similar idea. Our old friend used to be K here, but now we're using 1 over 4 pi epsilon naught Q1, Q2 over r squared. Basically speaking, these two formulas look very similar to me, especially last year we had a K value here and a big G there. All right, now we know the forces and how these forces operate. The next question is, what's the strength of the electric field? So we know that the generalized definition of electric field is the force divided by Q1. Q1 is the small charge, typically the test charge that we use to get the strength of the electric field. In gravity land, we take the force of gravity and divide by m1. That's the test mass, you know, whether it's a little pen or whatever we're using, and we drop it like so. Notice that the force of gravity is equal to m1g, duh. So we use that and think about g, the strength of the field, in terms of newtons per kilogram for the units. All right, now, electric field is going to be newtons per coulomb of charge. So newtons per kilogram here for that field, and then newtons per coulomb for this field. Now we can take these formulas and take the force formulas and divide by the denominator in gravity land m1, q1 in electric land, and we end up with this nice equation. Now this equation is excellent under certain conditions. If we look here, notice how the electric field is spreading out in a radially from the center. That creates a 1 over r squared effect where it starts to thin out relatively quickly. So if we were to look at, say, the electric field lines here, and we draw them in, I'll just put a few more in. Notice that I'm making this charge stronger by putting more lines in. So that's how we actually denote that. When we look at a certain spot here, let's say I draw a certain area, notice how many lines are going through that particular area. So in that area, we have the strength of 4 electric field lines going through. So as we move away, I'll draw the same size area out here, but notice when I'm far away, only 2 of the lines actually go through there. Shows that the electric field is weakening as we move away. And it's not just weakening, it's weakening as a 1 over r squared type function. All right, now, when we take a look at electric fields, all right, we can also look at a negatively charged situation. All right, so if we draw a negative charge here, this is our main charge, Q2. All right, and if we take out our test charge right here, Q1, open up your little box, take out the test charge. Yep, the test charge is a positive. Doesn't matter whether the large charge is positive or negative, the test charge will always be positive by convention. All right, so if I put a little tiny test charge here just to check out the electric field, we notice that the force is inward, so the electric field line goes in. If I do it over here, same thing. So these lines for negatively charged particles are always going to be towards the negative particle itself. This reminds me very much of gravity, where there's an attractive type situation, and in this case it kind of exactly looks like that. Now, what do we use for the formula for a negatively charged particle? Remember that these are absolute value signs. So this charge is whatever it is, whether it's plus or minus. This formula still applies, and the magnitude of the electric field, it really doesn't matter whether it's a plus or minus, the equation stays the same. The only thing that changes is the direction of the arrows, the direction of the field lines as we go through them. All right, now, if we look over here, we can also have a situation where instead of we having a symmetrical type situation, all right, we have, instead of a spherical situation, I meant to say, is let's suppose we have a couple of plates. So we look here, and these plates are charged positively, let's say on the top, and then negatively on the bottom, like so. Now, reviewing the field lines, let's get our test charge out, and let's see what the electric field is between 2 oppositely charged plates. Now, if I take a test charge and I place that positive right there just to check it out, doesn't the positive here push down on this one and repel? The negative down below also sees the positive and then pulls down, so we actually have the force both downward. So we know in the vertical direction that the force here has to be straight down here from those 2 particles. Now, let's take a look in the x direction, to the left and to the right. Isn't there a positive particle pulling the test charge, actually pushing it to the right? And on the opposite side, this positive is pushing it to the left. So for every one of these, isn't there a corresponding one on the opposite side? This one, this one, this one, this one. These all negate each other, so there absolutely is no force going left or right because they always negate. So as I keep testing all the way through this, I end up with these vertical lines. So the electric field strength here, if you look at this particular situation, the lines actually don't radiate out, they're actually straight. Now in real life you're saying, okay, I understand. All right, we've got a situation where, let's say we look at this side. So we've got a plus and a minus, and yeah, it's coming down this way, but aren't there a lot of positives off to the left side? And there's no positives to the right. Oops. It's not going to end up being straight down anymore. If we look here, there's a lot of negatives to the left, but there's no negatives to the right. So what's going to end up happening in real life, when we get to the ends of the plates, they're going to start to curl. So we end up with this situation where they actually end up curving. So at the end in real life, they start to curve. Many times in WebAssign, they'll just say ideal plates or whatever, and that kind of eliminates that side part to it, so you're basically looking at the center. Now, when I go to use the formulas to find the electric field strength, my tendency is to use this formula because I just love it so much, because this is such a great formula. 1 over 4 pi epsilon naught. Q2 would be the charges on the plate divided by r squared. So if I look at that formula, we've got a problem here. If I go back to my original idea here, doesn't that 1 over r squared come from the fact that the lines are radiating outward? So as I move away, they get proportionately weaker as we go out, because they're thinning out, because the lines themselves have to cover more area. All right, that's where the r squared comes from. If I look in this particular one, these lines never actually thin out. Aren't they always parallel to each other? The strength of the electric field is always going to be the same no matter where I am. And I'm going to get rid of this curling idea here and just take a look at an ideal situation. Isn't the electric field always going to be the same, because the lines themselves are always going to be in the same direction? This formula is no, no, no. No, no, no. Don't be using that, because it's not true. Who can we actually count on, though? If we go back to the definition of electric field, it's the force divided by Q1. So if we look here, the electric field is going to end up being F divided by Q1. If we look here, we can still find the strength of the electric field by figuring out the force on a particle that's inside that field. And there it is. There's our little Q1, this particle that we're trying to find the force on. So if we look here, we can now determine the strength of the electric field. And the nice thing is it's constant throughout the whole set of plates, so we don't have to worry about it. Once we get this, it's the same everywhere.